Thank you for coming. I want to set the context for those visiting us tonight, whether you're in industry or you're a parent or you're whoever else you are. I want you to think it's not 2025. And I want you to think if it's 1908. And we're having this little meeting in Detroit, Michigan. And you heard that they're going to display something called the automobile. It might change your life. And you go, we'll go. I think there's free food. Guys, that's the power of tonight times 10. And I don't need to be asked if that's correct because I know it is. This is what I do day in and day out. So you might hear how a transistor radio is built or the transmission inside of a car, or you might not understand it all, but know this. What these young people are going to educate you about tonight is the future of everything. And that's why this is so fun to be at the bottom of the first inning in this big game. Speaking of games, I want to take a minute to talk about our sponsors. So we had this crazy idea, can you bring private companies to the academic setting where it's not just a head tap and say, it's nice to meet you, here's your A, scram kid. No, we wanted companies that wanted real answers to these problems. Like, what is this AI and how do we use it? So this being our fourth semester and me being a sales guy, I've bragged a bit that we have the 1927 Yankees. Does anybody know what that means? Anybody older in the crowd? What does that mean, Brian Heyman?
They're the greatest baseball team.
Murderers Row. So when I say Murderers Row, folks, yes, I don't know who Babe Ruth is, and I don't know who Lou Gehrig is, but when you talk about the largest chemical company in the world, when you talk about Shell, when you talk about Entergy, who has one of the only chief AI officers in the country, who's here tonight, Andy Quick, where is he? There he is. And then when you talk about the lake, I mean, guys, how much better could we have done? But again, this wasn't a head tap. This wasn't a, hey, nice to be in your little college class. These folks, guys, all the four models you see tonight will be deployed at these four private businesses. And to Dean Colvin's point, think about the impact that these four guys have on the state of Louisiana. And oh, and by the way, these super smart kids who would have to run to Austin or San Francisco or Dallas can stay here. I need an amen on that. Thank you. Guys, this is one of the steps forward where Louisiana no longer is a 48th to 49th out of 50. Because to Roy Haggerty's credit, and I'll take 30 seconds to brag on my friend, as good of a provost he is, he's a better man. And guys, leave it to a hydrologist with a PhD from Stanford, Canadian, to come down to Louisiana and push us to the future, because that's exactly what that man has done. Without him, this does not exist. These opportunities for these young people don't exist. So thank you for making this happen. I'm not an academic, guys. I think that ivory tower thing comes from like people in his position sitting way up in it and you never see him. He was at every single class we had this semester. So again, couldn't say more. All right, what are you going to see tonight? You're going to see four presentations about 15 minutes long from our students that built these AI products based on the challenges they were given. We're going to do all four, and then we're going to bring them all back up for your questions, which you should have a few. And then afterwards, please, 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 adults, hang out, say hello, beg one of these kids to intern, although I don't know if we have many that are available left. But again, thank you so much for being here, and you're about to witness the future. So with that, let me bring up the BASF team, and we will get going.
All right, good evening, everyone. So tonight, thanks all of y'all for coming, and we'll be presenting ARI, the Artificial Retrieval Intelligence tool that we built. Our team consists of Benjamin Hun, Austin Luke, Jonathan Morse, Nathan Pham, Mark Stubbs, and myself, Edwin Sal. And we are sponsored by BASF. So a little bit about BASF. So BASF is located in Geismar, Louisiana. The Geismar site is BASF's largest manufacturing facility in North America. They have 32 production plants, and they house over 2,000 employees and contractors. Now, with an operation as large as BASF's, file management can obviously become an issue. So what are some problems? Well, for one, wasted time. So engineers and employees at BASF are spending, on average, about 20 minutes looking for files. And while that may not seem like a lot, it can add up really quickly. Another issue is with their file retrieval process. And that's mainly because it's still very ineffective and inefficient at this point in time. And then lastly, re-engineering. So whenever engineers are not able to find the files that they need to complete their project, they tend to just redo the whole project from scratch. And that's a lot of wasted time and energy. So next, I'll talk a little bit about what it currently looks like for finding files at BSF without RE. So this is Mr. Kerwall, one of our project sponsors and an engineer at BSF's Monomers division. And let's imagine if Mr. Kerr is on a project and he needs to find the technical drawing for a dryer model, like the one shown on the right here. Well, to do that right now, he would have to go look through all of these folders, and just when he thinks he has the right folder, all of the files in that folder are named in number strings and not in letters or words. And so there's no context to be given. And when that happens, Mr. Kerr will have to look through each and every one of those files to finally get to what he wants. And by the end of all this, Mr. Kerr is probably going to be very tired and frustrated. And he has probably also spent a lot of time doing this. And that's just not acceptable. Next, I'll hand it off to Ben to talk about our mission and the data cleaning that we did.
All right, thank you, Edwin. So yeah, let's get into what our and we wanted to improve upon past work that's been done to give better data cleaning, improve its scalability to potentially get all 4 million files at this Geismar site, and then provide an implementation at BASF in the future. So this is a little project methodology graph. It's the basic blueprint for how the system works. We start out with the 20,000 files that BASF provided us this semester, and we throw that into RE in these 3 distinct components: the pre-processing, the database, and the search. All of these components work together and utilize AI, state-of-the-art AI technology that we've learned about this semester. So the first part, pre-processing or data cleaning. Why do we care about data cleaning? What's the big deal? Cleaning's in the name. You can imagine it like a janitor. It does all of the dirty work that really no one wants to do, but it's absolutely critical for RE to work. And these were, you can't just throw these files into a database and call it a day. You need to transform them into a manageable, uniform data set that the computer can understand. And these were the tools we use at the bottom. I want to specifically point out Qwen 2.5. That was an AI model we used for image data. And also Tesseract was used for optical character recognition. And I'll get into a little bit how those work in the next slide. So for the actual process of data cleaning, we want to extract the text and image data from every file. And this semester we learned that image data is actually the most interesting, it's the most significant because it increased RE search results. So to do this, we use optical character recognition, or OCR. This just allows you to detect text and extract it from an image. And we also used AI vision models, Qwen 2.5, what I mentioned. This allowed us to create detailed descriptions of these images and put that into RE. However, this process of collecting image data takes a long time. So, getting better scalability to include all 4 million of these files is very important for BASF. So we learned that we need to shave down the files that we actually care about. And that's where this pie chart comes in. We processed 71% of the total 20,000 that BASF provided. And yeah, again, this is just important for the scalability aspect of this project. So now I'll hand it off to Austin to explain how the data is imported into RE.
All right, thank you, Ben. So now that we have our clean data, so what? Our data is still very unorganized. It's in nested files. It's very hard to find anything we're looking for. That is why we are introducing a database into our pipeline. In order to do this, we've been using technologies like Chroma and ParadeDB in order to create this database, and we're using PG Vector to allow this database to handle AI-powered search. So what do we hope to get out of a database in the system? Okay, so what we want is for our files to be organized in such a way that each file can be found in its own group with other files of related topic. This is because we want to be able to search and find the files that we're looking for without all the hassle of sifting through every single file that we have at BASF. Above is a scatter plot of every single document that we have implemented into a database. Each dot represents a single document that we have. So if we're looking at this scatter plot, our yellow group, which is titled Water Treatment Systems and Planning, that is our group where we will find every single document that is related to water treatment systems and planning. This is helpful for us because it eliminates a bunch of other groups that could have documents, but they're not related to our search, so we're not going to need them. Next slide. Now, how do we achieve this? Well, our data is clean, which is good for us because we can read English, but computers aren't very good at understanding just words. So what we do is we take our clean text documents and we turn them into a list of numbers with a specialized AI model. Now, this list of numbers sort of acts like a fingerprint for each of these documents. Each document has a unique fingerprint, and similar documents will have fingerprints that are similar to each other. We then put these fingerprints into our database, and what that does is it groups our data really nicely so that documents that are very similar to each other get put next to other documents. Now, before this system, we had a very unorganized, cluttered mess of nested folders that we had to look through. But now that we've implemented this, we have a nice, clean, and sorted warehouse where we can find what we're looking for based on what group we want to look through. Now I'm going to pass it over to Johnny to explain how our search works.
Thank you, Austin, for that awesome explanation. As Austin mentioned, having a vector database like that that's structured is critical to our application. But a good database is only as good as its search function. That's where we can turn to our search function here. To power this, we used Python to build out our search functions and Streamlit to build out a user interface to directly query our database. Now, I have a question. How many of you have spent more time than you'd like to admit looking for a file? Raise your hands, everybody. That's the exact problem that we're trying to solve. And for a professional like Mr. Kerr, that time is critical. And we not only want to deliver the exact documents, but the relevant answers for that. The search engine is what powers our system. Let's take a look at ARI in action. So suppose you're an engineer at BASF, like Mr. Kerr, and you want to find the relevant documents for handling a specific chemical. Let's just say in this example, we're looking for the safety protocols for handling aluminum sulfate. Now, we can directly interface with ARI, and in seconds, it searches through thousands of documents to find the most relevant ones. And here we have a concise answer that gives us exactly what we need. We can also view the citations and verify that what we're looking at is exactly what we need. That's the power of ARI. We're getting critical information like that. But what if we wanted a higher level overview of our database? What if we wanted to maybe see the distribution of file types in our database? Well, with ARI, we can also do that. Using its agentic functions, it can generate bar charts based off of the metadata that we hold in our database. But what if we wanted even more insights? What if we wanted to see more information about our documents? Well, we can turn to our Explorer and check that out. I'll pass it over to Nathan to take it from there.
Thanks, Johnny. Now, here in the Document Explorer tab is where users can perform general document searches. Behind the scenes, this tab uses a hybrid search system, which means it looks for both exact matches and technical terms related to the documents. Now, let's go over a typical use case. Now with ARI, Mr. Kerr can ask a question like, I need help disassembling a dryer model. And just like that, ARI returns a list of relevant documents all displayed here with some pretty useful details. Starting from our left or the left, we have the document's ID, title, and type. Next is the relevance bar. This bar helps rank how closely each document matches closely to the user's prompt. This is possible by using the clustering and the data cleaning, and this is helpful as it helps rank or prioritize the most relevant documents at the very top of the list, making it even easier for users to find the right documents. Next is a short text preview just to give the users an idea or feel of what they're looking at before actually opening anything. And if something does look promising, they can select a file and view it right inside the app to make sure that everything's finalized before actually using the document. Now, I'll be passing it over to Mark.
Thank you, Nathan. That was a great demo. So, now that you've seen Ari in action, let's talk about how well Ari is actually performing. And the best way to do that is to look at how accurate our search is. We were able to achieve an accuracy of 82%, which means that that is how often we were able to get the correct file on the very first search. This is the power of Ari, being able to reliably and very quickly retrieve important information for everyday use at BASF. Now, despite this, Ari isn't perfect. Currently, we're processing files at an average rate of 24 seconds for just a single file. Now, to put this in perspective, just as Ben said earlier, they have over 4 million files just at the Geismar site, and that would take over 4 years to process. Now, that's going to make Mr. Kerr even sadder than he was before. And so, luckily, we've actually found a way to combat this, which I'll talk about a little bit in the next slide. So, moving forward at BASF, how are we going to continue to develop what we've already built? Well, first, I want to address the biggest issue that I just talked about, which is the file processing time. Recently, we discovered this tool called Apache Tika, which is able to clean and process files in a very similar way to Ari, while not utilizing AI and being much, much faster, over 20 times as fast. However, because it does not use AI, it is unable to process visual modes of information, like images, schematics, and diagrams, that are so important to work at BASF. This is why we're moving forward with a hybrid approach. This semester, we learned that not every document needs to be processed by AI. There is simply too much data and it takes too long, which is why we're moving forward with this hybrid approach. In the same vein of speeding up Ari's file processing, though, we're also going to implement parallelization, which is really just a fancy way of saying that we're going to split the heavy and intensive workload of the AI over multiple computers so we can speed up how fast we're inserting new files into Ari to search on. And lastly, we're going to expand on the types of files that Ari is capable of processing in order to expand the knowledge that BASF employees are able to search on in their day-to-day work. And lastly, I want to mention that all of this is currently in the process of being implemented at BASF today. Now I'd like to hand it back over to Nathan for some closing statements and acknowledgements.
Thanks, Mark. As we're closing out, we'd like to give a couple acknowledgements. First, we'd like to thank Mr. Kerwall, Mr. Eric Dixon, and Will Canup from BASF for helping us throughout this whole process. And we'd also like to thank Kyle McCleary for helping us on the coding development. Finally, next slide. Finally, we'd like to thank you all for your time, and we hope you enjoyed the rest of the night. This is Ari. Thank you all again.
Hi, everyone. My name is Lakedra. This is Sam, Muhammad, Hudson, Lauren, and Zach. And we also have another member, Skylar. He wasn't able to make it today, but we are Eric. So why are we here? Over the past semester, we've been working with Entergy. We've been working with Entergy to share this project with you today. So who is Entergy? Entergy is a major energy provider that focuses on growth and improving reliability and resilience in their infrastructure. They are a Fortune 500 company, and they have over 3 million customers. They are located in the South, Louisiana, Mississippi, Texas, and Arkansas. Their headquarters is in New Orleans, and they have 12,000 employees. All of this is just to give you a sense of how big their role is and why our work with them is very impactful and exciting. So this is where things get real. Let's talk about Hurricane Ida. In 2021, Hurricane Ida was a Category 4 storm that caused massive damage. Over 1 million customers lost their power, and it was recorded as one of the highest outage events in Entergy's history. But what really stands out is Entergy's ability to restore for restoration. Whether it's a small outage or a big storm, Entergy is able to mobilize teams and resources fast, showing their commitment to reliable power. Now I will take it over to Lauren, who will give us our motivation.
Thank you. So if you've lived in Louisiana or the South in general for a while, you probably have your storm preparedness measures down to a T. By the time that storm warning hits, you're gathering all your portable chargers and generators that you have, and then you're lugging those jugs of water from your car to the innermost room in your home. Now, what is Entergy doing during this time? During this time, Entergy is preparing their scouts who will go out and report and assess storm damage done to their infrastructure. This information is used by their linemen who will then go out and make any necessary repairs in order to restore your service. Now, something to mention is that when the scouts go out, this is manual work. They have to manually inspect and fill out documentation for each part of their infrastructure. But when we use ERIC, which is the product that we developed, an image can be uploaded by an Entergy team member, dash cam footage, or a member of the community that notices damage. This image is then fed to a fine-tuned model that will not only report on the condition of the asset, but also the quantity of each component in the image. Now, in a nutshell, our goal was to create a product for Entergy that will make their storm damage assessment procedures more efficient. Accomplishing these objectives will not only decrease the downtime for their customers, but it will also save Entergy money and be more cost efficient. These costs are incurred to Entergy through having to pay their teams extra time for the time they work during the storm, as well as housing and feeding them during this time. And a very important thing to mention, this will greatly increase their customer satisfaction by decreasing the downtime of their service. And now I'll pass it to Zach to go over how we actually did this.
Thank you very much, Lauren. So, I would just like to go over how ERIC actually works. So, let's think of a scenario. First, an image will be submitted to our front end by any user. And from there, it will be sent to our back end where it will be processed for additional information and also downsized. At the same time, it will be sent to our AI, where it will be processed and assessed for pole damage and to its individual components. Once all the information is compiled, we will save it to our database. And from there, the user can go to their front end and access all the information where it will be formatted into an inspection report. Now I'd just like to go briefly over our tech stack. For our front end and back end framework, we use React and Fast API respectively. For our AI processing, we use an OpenAI LLM agent. For our container service, we use Docker, and for our version control, we use Git. For our database, we use PostgreSQL. Now, for what you've all been waiting for, I'd like to hand it over to Hudson for our demo.
Thank you, Zach. Hello, everyone. My name is Hudson, and Mohammed and I will be demonstrating some of Entergy's features through our interactive demo. So let's check it out. So here's our homepage. These are all snippets from our web application, and it just gives a brief description about what ERIC does and a little bit about who we are. So let's scroll down and check out some of our features. So here we see some of our features, our inventory, our map, and our upload, which is how we're going to start. So let's start with uploading. Check it out. Here's our upload page. Here's where users would drag in images of damaged poles, which will then be assessed by our AI. So let's start that now. Let's drag in our image, and let's start the processing now. So we're going to upload it, and right now our AI model is going to be analyzing different components and basically assessing the damages of each of them, right? So here comes the inspection report, right? So here's our output. But before we look at the AI results, let's take a look at the pole itself. So obviously, it's not in the best shape. We can see that the main structure is leaning, and some of the wires have fallen. So let's see what our AI has picked up, though. Let's scroll down, and here we can see all the different components we're searching for. And we can see, for example, that it did pick up that the main pole is bad, and it gives a reason why it's leaning, right? And you can see also it says the secondary wires have fallen, but for the most part, all the other stuff is still intact. So let's continue to our database, where we could find all the different poles we've assessed and added. So here is all the poles we've been analyzing for the last couple months, and let's find the pole that we just added. So let's search by the newest, and let's find our pole and view more details. So here we're going to view more details, and we're going to look at our inspection sheet again, but now it has a annotated image. This makes the data easy to share, right? So you could just send an image to somebody and see the different components it's picked up and the damage it has, right? As well as all the other components as well. So yes. Now let's test out some filtering. So let's go back to our query table and let's filter for, let's say we're looking for images where the main pole structure has been identified as good. So let's click that. And right now you can see that our database is a mix of a bunch of different conditions. But once we click search, we will filter through all the poles and find only images where the main pole structure is good.
All right, thank you, Hudson. And now we also have one more type of filter, and that's for location. So if we go and we filter for images that have location data only, and we select the first one, we'll see that we have a new button over here, the View on Map button. So whenever a picture is uploaded, our system tries to automatically extract the location metadata, and if it's present, we get this View on Map button. So let's click it. We're taken to this map page, and we're going to zoom into this specific pole, and we can see that it's highlighting which pole we just clicked on right there. And so this will help contractors find exactly where a pole is and to get a sense of the damage on the neighboring poles as well. However, this map isn't just for looking at single poles. If we go back to our home page and we scroll down again, we have the map button. And going on the map page brings us to a similar page, except now we have all the poles that have location metadata. All of them will be visible on this page to give us a good overview of the condition of the system after a storm. So let's zoom in on one of these. We can see that when we zoom in on this pole, it has a green outline. That means that the pole is in good condition. So when we click on it, we of course see it's in good condition. But if we go to a different pole, such as this one, we can see it has a red outline. And clicking on it, of course, tells us that the pole is in poor condition. Now, as before, we have this annotated, easy-to-share image, and we can also scroll down on the sidebar and get a quick overview, get a quick description of what exactly is wrong with the pole. If we need more information, we can click the View More Details button, which will bring up all the info we had before. Now, the map also has a satellite imagery feature. So if on the bottom right we turn on the satellite view, we can see that all of our poles are now overlaid over real satellite imagery. We can, of course, also switch back to the 3D building view. And having both of these options will help us get a better sense of how the system is after a storm and aid with faster recovery. And now I'll pass it off to Sam for results.
Thanks, Mohammed. So before we get into the actual results, I want to define two key terms for you guys. First, we have quantity, and that is going to be how many instances of each component is actually present in the image. And then we have condition, which is a classification being good, bad, or unknown if the component isn't actually present. So we're going to start with quantity accuracy. Now this tells us how often the model was exactly right in its count of a component. So you can see we achieved an overall score of 77%. Now if we look at our highest performance in polls, we can see that it got all of them. And that makes sense, right? They're large, distinct, not hard to point out. It's a poll. So this also tells us that the model is capable of focusing on the foreground of the image, where the target infrastructure is going to be for analysis, instead of getting distracted by background clutter. Now, if we look at our lowest score, insulators, this is going to bring up two key challenges. That's going to be component complexity and visual variance. Because LLMs rely on pattern recognition, we're going to need to train with more examples covering every variant of what an insulator can look like. So next up, we have condition accuracy. So you might think, why is the score like 11 points higher than quantity? Well, there's a good reason for that. Most of our data consisted of infrastructure that was well maintained, so the model got really good at classifying good infrastructure. So the good part is this is going to translate well into bad infrastructure. So with more examples, you're going to find increased performance. So now back to Lakidra for some closing thoughts.
Okay, now on to Eric's impact. First, Eric will allow for more accurate material counts. When there's damaged poles, crews can go out into the field. They need to know what they need to bring and how much. But with Eric, this allows for more accuracy and they don't have to just guess. Next is smarter tracking of damage and replaced equipment. This allows for better field visibility and reduces delays. Next, it reduces the need for scouting. Instead of going out into the field manually, going down the line of damaged poles, Eric can accurately view those images and mark what's wrong with them automatically. And because of this, Entergy doesn't have to hire a lot of scouts. They can use those people and those resources for better things. And overall, it really isn't about technology, it's about getting your lights on, So Eric can already do some pretty cool stuff, but we have more. If we had more time and investments, we'd like for Eric to be able to use videos instead of just images to detect storm damage, think drones and security camera footage. Next, we would like it to order and stage materials. This just means that Eric will be able to identify what needs to be replaced. It'll be able to order it and have it prepared to be put in the field. So it's basically like Amazon Prime. Third, it'll be able to track work orders and materials. You'll be able to know what needs to be done and what's already done. And finally, we want to integrate it with Entergy's GIS mapping system. It'll be able to compare what's already in the field to what should be there. Okay, and thank you to Entergy for working with us through this project. And thank you guys, you can contact us here.
Tonight, I'm Macy, this is Ricky, Aiden, Caitlin, Logan, and Andrew, and we are so excited to present our project, Policy Portal, for you tonight, which we made for our sponsors at Our Lady of the Lake. Our Lady of the Lake is a branch of the main healthcare system, the Franciscan Missionaries of Our Lady Health System. This system spans between Louisiana and Mississippi and has grown to become one of the largest healthcare systems in the region. Our Lady of the Lake specifically is located right here in Baton Rouge, and it serves about 820,000 individuals annually just in its outpatient locations. It also has about 2,900 active physicians and about 7,500 active employees, like Nurse Jessica here. Nurse Jessica will be our hypothetical nurse example throughout this presentation, and she faces a common problem that a lot of Our Lady of the Lake employees face of not being able to find certain policies that they need on a day-to-day basis. Currently, these policies are hidden under a SharePoint file that's really hard to focus on and go through. In short, it can be like trying to find a needle in a haystack.
So, we mentioned a needle in the haystack situation. What does that look like on a day-to-day basis, and why is it such a big problem? Well, before Nurse Jessica can treat anything, she needs to first sit down and search through a database. There, she's going to find a specific policy that corresponds to the situation. This is done in order for proper protocol to be followed, as well as to operate within legal boundaries. However, to do so, she runs into many challenges, such as poor search capabilities, inconsistent file types, vague or identical file names, or poor access to the actual file content itself. All of this creates frustration for Nurse Jessica, as well as hundreds of other hospital workers at Our Lady of the Lake. This also leads to critical time being wasted when seconds could determine patient outcomes and conditions. On the administrative side of things, Our Lady of the Lake must annually undergo an audit to ensure proper protocols are being followed. However, to do this, a worker must follow the auditor with a thick binder of printed out policy sheets, which is quite a sight. So, in summary, this process creates employee frustration, potential legal liabilities, as well as slower patient care.
And so to address these concerns, we created Policy Portal. Policy Portal is a chatbot used to retrieve information from official Our Lady of the Lake documents. Instead of having to dig through complex directory structures and ambiguous file names, all Nurse Jessica has to do is simply type in a query, wait a few seconds, and in front of her, she'll have an answer that's not only concise, but also contextually correct. This increases productivity and allows Nurse Jessica to focus on more important things like the patients rather than digging through complex files. Furthermore, with the ever-changing policies that hospitals have to go through, we've made our policy portal able to be integrated into a bigger entity and a bigger healthcare system. That way, it's not restricted to just our Lady of the Lake. It can expand to the broader healthcare system.
So to show why these improvements matter in practice, let's consider what it looks like to find a policy without our product. Imagine Nurse Jessica urgently needs to find a specific policy surrounding fire codes, something that she doesn't have access to often. So without our streamlined system, she would have to log into the SharePoint, navigate to the Lake section, and then go through multiple nested folders to find a vaguely named policy like ECLS000.doc. This process is long, frustrating, and unintuitive, especially in a time-sensitive situation. That's where our product, Policy Portal, comes in.
Now, let's see what the search looks like with Policy Portal. Let's say Nurse Jessica has a question about fire safety. Her question might look like, what do I do if my department has a code red fire emergency? First, her question will go through the system, and it'll be embedded, which essentially just means her question will be turned into a long string of characters and numbers, and then sent through the database so that the computer can understand. So it becomes embedded, and then it'll search through our database, find similar documents, then it'll be cited and summarized, and with the correct document in the summarization, it'll then spit it out to the user. Now what do we use to make this? First, we use Parade DB for our database. Then we use BGE M3 to vectorize all of our queries and use it to make our vector store. Then we use HTML and CSS for our user interface, and we use ChatGPT, OpenAI's ChatGPT 4.0 for summarizing and formatting our answers.
So this diagram is basically just a much more expanded version of the methods that Logan just covered. And I know it's a lot, but don't worry because there's actually no need to go through every step of the diagram. As an overview, it's just the pipeline that we use to create our product Policy Portal. For those of you that like to dive into the technical details, we use technologies such as RAG, OCR, and vector search.
So like Logan mentioned earlier, what if Nurse Jessica does have a question about a code red fire safety plan? Let's say for this example, she's curious about the pre and post-op areas and what to do in this situation. Rather than actually searching through the big binder that Ricky mentioned earlier, she can just ask Policy Portal. And as you can see, it spits out in just a few seconds a nice formatted response for the user. In our bottom bar, we have a nice scrollable, formatted section that includes all of the sources that are clickable and downloadable for the user to view in either a browser or in Microsoft Word. Also, if you notice in the actual body of the response, you can see the inline citations. These can be hovered over, and you can actually see the exact source and what quote was used to actually make that particular answer. So moving on, let's see what if Nurse Jessica now has to help someone in the emergency medicine department. And she's curious about what to do, and instead of having to reformat the question and come with this another long question, she can simply ask a follow-up question since all of the questions are actually contextualized with the previous chats. And as you can see, it actually says, I'm sorry, I don't have enough information to answer this. This is not a flaw, but it's actually by design. We don't want Policy Portal to give a response that may be false or hallucinated in any way, since integrity and accuracy is extremely important when it comes to Policy Portal. And continuing on, let's now check out our dark mode. As a young person, I thought dark mode was an absolute necessity. You have to have it. Thank you. You have to have it, but if you want to go back to light mode, you can go back. You will be judged. But moving forward, what about now Nurse Jessica has to deal with a really stressful situation like a code blue at a hospital for someone that's actually going into cardiac arrest. This can be very stressful, and Nurse Jessica maybe forgets a key part, but doesn't have the time to actually go look through all of these documents. Instead, she can ask policy portal and get a response in seconds. Whether she does have to just double check or if she's audited to get the entire document, she can simply ask policy portal and get an answer in a matter of seconds rather than doing that super long search. And as you can see, there's a very detailed and lengthy response for this extremely stressful situation. Each paragraph has a bolded title so you can easily find and navigate through the entire text, along with those inline citations that I mentioned earlier. Also, we can actually download these policies, like I mentioned earlier. I wasn't lying. And unfortunately for the demo, we actually can't show them since they are proprietary to Our Lady of the Lake.
So thank you, Aiden. As you could hopefully see, this will have amazing impacts for Our Lady of the Lake, and we hope that it can make a big difference in their day-to-day process. People like Nurse Jessica would likely spend a lot less time trying to find a policy than they would under the current system. They would also probably be way less frustrated and more satisfied because they're getting to spend more time with the patients. And finally, this would be much more cost-effective for Our Lady of the Lake because they'd be paying people for not simple tasks, but things that they were trained to do. This would also be super helpful from an administrative perspective for the audits at the end of the year. And it would help Our Lady of the Lake achieve its main goal of improving patient outcomes.
So although Policy Portal does increase the access to policies and procedures at Our Lady of the Lake, we do want to address the potential concerns that our chatbot does introduce. And those possible conflicts is transparency and security. To address transparency, we try to ensure that our chatbot is as transparent as possible. Because in a healthcare setting, patients' lives are on the line, and so we want our chatbot to be as accurate and transparent as possible. To ensure this, we have our chatbot introduce inline citations, links to the original documents, and if our chatbot doesn't know how to respond, it will be honest and transparent about it. This ensures that it's reliable and credible and ensures that there are no hallucinations or false information. Now, on the security front, we also ensure that our chatbot only pulls from Our Lady of the Lake specific documents only. It ensures that it pulls information from those documents only. Because if we pull information from outside sources, those might conflict with Our Lady of the Lake procedures and policies. So we ensure it only pulls from Our Lady of the Lake policies. This ensures that our chatbot is specific to Our Lady of the Lake only, and ensures credibility and reliability.
So as you may be able to tell, our group has accomplished a lot this semester, and we believe that we have made a really good solution to Our Lady of the Lake's problems. However, given some more time and resources, we would like to make this project as good as possible. The first way is by retrieving the latest documents. As it stands right now, Policy Portal only has access to what we actually give it. There's no automation in updating with the newest policy. So if a policy was updated last week, Policy Portal does not have access to that current information. Next is enhanced data cleaning. Policy Portal can extract data from a lot of different file types, mainly PDFs and docx file types, but we would like to expand this to many others or streamline the data cleaning process to make the entire process faster and more efficient and allowing for the best data extraction. And lastly, and our most ambitious goal is scaling up. The plan right now is to implement Policy Portal into Our Lady of the Lake, but there is hope that we can implement this across the entire health system to ensure that patients' lives we help more and more patients and help the lives of the physicians as well, doing all the hard work.
Before we close, we just want to give a big thank you to our sponsors at Our Lady of the Lake, specifically Dr. Jagno, Will Landry, and Charles Beam. Thank you guys for your constant support of this class at LSU and for being such an amazing part of the Baton Rouge community. Thank you again for your time.
Alrighty, howdy y'all, I'm Garrett Wainwright, and welcome to Team Shell Yeah. Thank you. Up here I've got my team. This is Fuad, this is Serene. Over here we have Cameron, Madison, Damian, and Hamad. And they did some incredible work this semester to help build a tool for Shell in their compliance area. So first, let's get into who Shell is. Shell is a multinational organization that handles a majority of the energy and chemicals processing within this global economy. So at Shell, they have 96,000 employees, which is a lot. And those employees bring in over $300 billion on average in yearly revenue. And specific to our project, they move 1.6 million tons of polyethylene annually. So that's a lot of polyethylene. But the problem then becomes, how do we ensure that we're not losing any of it, right? Rail cars carry very volatile products. A leak in a seal, a break in a seal. I mean, these things could have not just significant cost impacts, but environmental. I mean, this could damage an organization reputationally, cost-wise. I mean, there are a number of ways that we need to make sure these seals stay sealed. So we use seal tags. On the board, you can see I've included 2 seal tags, one for a top seal, one for a bottom seal. They go through all 3 holes, and they make sure that they're facing, they're locked down, and they're secured. So sometimes these seals can be broken or just plain bad. And because there's 18 of them per rail car, they're often just gone. So meet Michael. Michael is a rail car inspection technician. Michael is perfect at his job. All right, he's never missed a seal a day in his life. He's never let a bad seal go past his rail yard. Michael is the man. But one day, the unthinkable happens. Product is spilled beyond his rail yard. And under our current system, the only thing we can use to verify that it wasn't Michael was his signature. Right? But his signature is what? So he's blamed. Even though he was perfect, he did everything right, and he signed off to ensure compliance, he's still blamed. This is a systemic issue. It's not just a problem in what Michael did, it's a problem in the whole process. Michael's perfect, we know this, but under our current system, he's in a he said, she said. So we're going to explain how we used AI verification to solve Michael's fundamental problem. We're going to pass it off to Hamad, who's going to explain how we did it.
All right, thank you, Garrett. Okay, so I know this may kind of look like a lot, but just bear with me here. I'm going to walk you guys through the main parts of our entire workflow. So as Garrett was saying, Shell came to us with this problem, and they wanted us to make an AI solution in order to make Michael's life just a little easier. So they wanted us to create a whole AI vision learning pipeline in order to automatically detect these faulty railcar seals and then notify the technicians on site if any flags do arise. And so obviously, this process starts with capturing the images on site. And so once an image is captured, it then gets sent into our storage system and then goes through a little pre-processing step just to ensure that the quality of the image is good enough so our model is able to evaluate it. And so from there, it enters our model, and depending on whether or not it is an image of a railcar seal or a railcar ID, the model returns a structured output containing things like the status of the seal, the railcar ID, or the railcar number. And so that structured output then gets sent into our database, and from there, our reporting system retrieves all the necessary information it needs in order to create its dashboard. And so from this dashboard, technicians can go see if any seals have been flagged, and they are also notified via an email if a seal has been flagged. So let's say a flag arises, Michael can just go into his email, click the resolve button, and that will be updated in our database as well as our reporting system. But let's say no flags arise, the railcar should be good to go, and we just made Michael's life a whole lot easier. Rather than him having to go in and check all 18 seals himself, it's a lot of work. Just with one snap of the camera, the whole entire process is done for Michael. But because this is not a perfect system, if an issue does arise, Michael is still there to solve it. So that's kind of a basic overview of how our product works. But now we're going to delve into more the technical aspects of our solution, starting with Cameron, who's going to talk about how a photo flows from one place to the next.
Thank you, Ahmad. So I want to talk more about the actual pipeline and how it's going to work in production. So first, our railcar is going to go into its bay, where it's going to hit an optical sensor, which will detect that there's a railcar in our bay so that we can start taking pictures of all the seals and railcar IDs. So then we're going to take a picture of each railcar seal and each railcar ID using cameras. And after we take a picture, it's going to be sent to our blob storage, which is like a giant 5-in cabinet, which stores all the images relating to a railcar. Now, how do we organize all these images? So since each railcar is in its bay for about 30 to 45 minutes, this provides us a pretty reasonable time window to put all the images in its proper container. So then, as each image is in the blob storage, it'll then be sent to our model, which we can use to extract the railcar ID, check to see if the seal is on there, and other information. Once it's in the model, then we'll take the output from the model and send it to our database. Once it's in our database, then depending on the output of the model, we can, if there's any faulty seals or if the railcar ID is missing, then we have to send an email to a technician, such as Michael, so he can go out and resolve the issue that happened when extracting the information from the model. After the information is in the database, then it's going to be automatically populated into our Power BI report, since everyone loves numbers, so that people can see how our model is doing and evaluate the performance. Now, to pass it off to Madison, she's going to talk more about the model.
Thank you, Cameron. Now for our initial model selection and creation. So overall, we have a RAG tool picker. RAG stands for Retrieval Augmented Generation, and essentially what this means is that we give the model a very long and detailed prompt so that, based on the image it is given, it will determine the appropriate tool to use. One of the two tools that we have is a seal model. So this uses OpenAI's GPT-4o Mini along with another very long and detailed prompt so that, based on the images given, it will determine the seal compliance of a hopper car. The other tool that we have is an ID model. This also uses OpenAI's vision capabilities along with another long and detailed prompt. Instead of this prompt is specialized in extracting IDs from hopper cars. As mentioned beforehand, this makes Michael's life a lot easier because instead of physically going out on the field and getting the compliance of these hopper cars or physically getting the IDs of these hopper cars, he can just tell the model to do so and it'll do it just like that. And of course, if there's any issues that arise from using this model, Michael will always be there to fix them. Now I'm going to hand it off to Damian, who's going to kind of describe the refinement of this RAG model.
Now, Madison has come up with the best prompt or set of instructions for the LLM, but this LLM is very general knowledge trained on data from all over the internet. We want our model to be an expert at the task at hand, like Michael. We can do this through a process called fine-tuning. Shell has given us hundreds of real-world images labeled as either good or bad. We can feed these examples into the LLM and it will learn from it, increasing its accuracy over time. Next, we use a method called hyperparameter optimization. I want you to visualize an old school TV with many knobs and buttons that control things like color, brightness, sharpness. We can adjust these accordingly to find the best settings for the video that we're watching. Behind the scenes of our model, there are many formulas, each having hyperparameters. We change these over and over again, each time looking at what the model has gotten wrong and its accuracy metrics. Through this, we have increased our initial model's accuracy of about 50% to 90%. Now that we have confidence in our model, Serene, what happens when it detects an anomaly?
Thank you, Damian. As many of us here know, AI systems are on the rise of being built every day, but how often are these systems being built with an override option? We decided to incorporate a notifier and resolving system for Michael to be able to be alerted as soon as a flagged railcar enters the database so he can fill out a form where he can override certain fields in our database. Through building a Power Automate flow that triggers as soon as a flagged railcar enters the database, Michael will instantly receive an email with the specific railcar's information, such as its ID, the time it was detected, the flag reason, and the ability to view the photo. Now this is where things start to get really good. Within this email, Michael can click that Resolve Now link where it'll take him straight to this Power App form where he'll be able to handle any missing IDs, upload fixed images that will instantly return back to our blob storage, and update any railcar seal status. This is our railcar dashboard built into Power BI. So now Michael and any employee in the office will be able to access this Power BI report, which will show metrics and analytics, such as the total rail car scans and how many of those scans were flagged, and if they still need action. And if they want, they can also access that Power App link within this Power BI form. And it'll also just show basic breakdowns, such as how many good versus bad seals there were, and whether they were AI detected or user overridden, and our current processing status across multiple sessions. Now I'm gonna hand this over to Fahad for our demo.
Thank you, Serene. So now you know why and how we built this system. Let's go ahead and see it in action. In this demo today, you're going to be seeing us manually upload pictures and images of these rail cars just so we could simulate our automated workflow, which would be taken with cameras. So first, we're going to go ahead and upload a rail car ID. So the rail car ID is on the back of a car. A camera would take a picture of it, then it would get analyzed by our model. So it takes around 7 to 8 seconds to send into our blob storage and around 2 to 3 seconds for the AI model to actually analyze it. And as you can see, it analyzed it properly. So next, we're going to go ahead and analyze a rail car seal, which is in good condition with Shell's policies. As you can see, it's properly on. It goes through all 3 loops, and it's at the bottom of the rail car. So once it's analyzed, it's going to go ahead and be sent into our database with no flags at all. Our next one that we're going to be analyzing is a bad rail car seal. So this bad rail car seal is completely off the bottom. It doesn't go through any of the loops, and it's just not in compliance with any of Shell's policies. So as you can see, once it's uploaded, it will be analyzed as improperly attached, and it will be sent to our database with flags. Now, Michael will actually get this email, and as we've said before, he can go ahead and click the link at the bottom of that email to go ahead and resolve it. This is really good because then Michael can go out into the field and actually take a picture, fix it up himself, and update the status of the seal, which would then get sent back into our database as a user-resolved seal. So once this process is done, we're going to go ahead and move on to our dashboard. So our dashboard, again, is just a big overview of analytics regarding our rail car session. So it provides analytics on things like the total amount of rail cars, as well as the comparison between improperly and properly attached seals. It also includes the analytics about pictures that weren't able to be processed just due to the fact that the picture could have been blurry. This is really good because then we can go and fix those ourselves physically. So having a structured organization like this is really, really good, but it's also really good for Shell as they can have a complete auditable record of every single process or every single image processed, which increases their security as well as their traceability. So now I'm going to go ahead and pass it off to Garrett for closing thoughts.
All right, so now that you know how it works, I invite you to take a step with me into the future of what it's going to do. It's going to change how Michael does his job. He's going to be more confident in how he does it, more confident in what he can do, and ultimately, it's going to make him do his job better. So this makes a really happy Michael, but it also makes a really happy Shell, who can now confirm that compliance is ensured in all of their rail cars and rail yards. And most importantly, we're going to end up with a better world. I mean, the seals are great, but if we can ensure that they are still together by the time it hits the next rail yard, I mean, we can save on pollution costs and ensure that we stay safer going into the future. But if we had more to invest, here you'll see a very detailed photo of a railcar seal. It has a really tiny number that connects it to all the other seals on the car. And if we had more to invest in more camera quality, we could likely go through and extract all of these individual identifiers on the seals and ensure not just complete compliance throughout a single car, but complete compliance throughout a single set of seals. And this would also help us with co-location, which is where we can not just see our order of cars in our database, but this would connect to a broader system within Shell that would extrapolate that data into a different GIS system that would allow you to see the cars where they are in the yard and beyond. And so this could be then scaled far beyond into many systems and many rail yards across the country to ensure that obviously we stay compliant everywhere. So this is my team. They built this tool. They did an incredible job, and these are their names. I encourage you to write them down. The tool that they built is impressive and robust and creative, and I'm very proud of what they did, but it wouldn't have been possible without also our Shell team. We have with us tonight, we have Miss Rachel, and of course, we have Michael, our glorious technician. Thank you. Shell, yeah.